Hello, my name is Mikhail Dvorkin. I am ICPC Gold Medalist and Kotlin enthusiast. In this short video, I will be solving problem 3, Toboggan trajectory from Advent of Code 2020. Let me guide you briefly through the problem statement. There is some area partially covered with trees. On this picture, a hash sign represents a presence of a tree, and a dot represents an absence of a tree. We see in the problem statement some sample rectangular area. And if we open our own input file, we also see a large rectangle with trees and empty spaces. But the actual, so to say, forest described in the problem is not a rectangle, but an infinite stripe. That is, our original rectangle is present once, and then it is repeated in the same fashion to the right of the original instance, and then once again to the right, and so on, forming a stripe that goes infinitely to the right. We start in the top left cell that is promised to be empty and move linearly in the down right direction through this stripe. The slope at which we are moving is a constant given to us in the problem statement. That is, each time we move 3 cells right and 1 cell down. After some amount of moves, we will leave this stripe of trees, and the question is how many trees we encounter during this procedure. Remember that the problems in Advent of Code always consist of 2 parts, and this is just part 1, so let's start solving it in Kotlin. I am implementing the main function, and I start with reading the rectangular field from the input. To do that, I address the file with the input from the base of my project folder structure. And with this file, I can run readLines function that will give me the list of strings, exactly how I want to represent a rectangle of characters. And let me first code in the old school imperative fashion. That is, I implement a mutable integer variable into which I will count the number of trees I encounter during the linear movement. I want to iterate with the y coordinate through all the rows of the rectangle, that is from 0 to the vertical size -1. However, this construction is not very readable and prone to +-1 mistakes, so I'd rather change it to the more readable and error-prone version. Now, for every y-coordinate, let's find the x-coordinate of the point of our linear trajectory in this row. The slope is 3 to 1, so the general formula is y times 3. But as we move quite far to the right, we will eventually leave the original rectangular area. So the x-coordinates should be brought back to the range of the original rectangle. That is, instead of each x-coordinate, we should take its remainder modulo the width of the original rectangle. So let's introduce the variable width, which is simply the length of the first string in our list of strings. And now, when we know the cell we visit in each row, we want to check if this cell contains a tree, and if so, increase the counter of trees by 1. Now we can print the number of trees, and if we run this code, we already receive the correct answer to the first part of the problem. But let's get rid of this mutable variable. I want to refactor it by saying that I take all the y-coordinates and count those of them that do indeed have a tree in a corresponding cell. Let's submit our answer and deserve to move to the second part of the problem. Here we have several slope directions that we need to process. One of them is the previous one, and a few new are introduced, including the one that moves 2 cells down each time. The task is to calculate the number of trees encountered if we use each of these 5 slopes and multiply together all the received numbers. Let's copy the list of slopes and get back to our code to enhance it to solve the second part. I want to have the list of vectors of our slopes, so I start with a multi-line string with the copied text, and I remove the explanation, and I press Ctrl down to enter the multi-line caret mode. In this mode, it is easy to edit the multi-line text to receive a well-syntaxed list of integer pairs. However, we are not paid by the number of lines of code, so let's rather press a wonderful Ctrl-Shift-J to receive a single line with all this content. Well, our previous code was successfully solving the problem for the specific slope 3,1. So let's extract the previous code to a function to make it more general. I'll call this function solve, and I press Alt up to move it above the main function. This solve function was working with the slope 3,1, so let me introduce this pair as a parameter to the function and call it vector. And let me use multiple assignment to receive the coordinates of this vector as integer variables. For most of the slopes, we can just replace the 3 with dx, and the new code will cover those cases. But we also have the slope 1, 2, and let's think deeper about it. When using this slope, we only visit the cells with even y coordinates. So in our iteration, the odd y coordinates definitely do not make us increase the tree counter by 1. And for even y coordinates, we just correctly calculate the corresponding x coordinate and reuse the previous code. How do we check that a y coordinate is appropriate? Well, it should be divisible by dy. Indeed, when dy is 1, all y coordinates are useful, and if dy equals 2, only the even ones are used. Now let's recalculate the x coordinate if dy is not necessarily equal to 1. Well, we move right dx cells not at each y coordinate, but only at the useful y coordinates, and the number of those can be calculated as y divided by dy. I think it's nice to have a code that is quite general and will work with various slope vectors, and let's check that it still works for the given slope 3,1. Now, for each slope vector, we can run the solve function to calculate the number of trees we encounter when using these slopes. And we receive the list of integers that we are to multiply together. That can be done by using the reduce function and specifying that we use multiplication as our reduce operation. Let's run our current code, and very fortunately for us, we obviously run into an integer overflow. Because we are multiplying several reasonable integers, and the result doesn't fit to the 32-bit integer type. Well, the number of trees each time will be low, so I don't want to change the return type of the function, but the received integers should be cast to a larger type that will not fail during the multiplication. And we see that the type long would be enough, but I'd rather leave big integer over here as it's safer and more usable in case someone uses longer list of slope vectors over here. So we can now submit our answer and enjoy the 2 gold stars for this problem. Thank you for watching this video. Solve problems, use Kotlin, have fun. Goodbye.